So welcome back. So my topic is concept of energy to conclude on stability and to establish the theory of Lyapunov. So I'm taking the same example as I've taken as before, the mass spring system. That example, okay. So the same state space equation, same differential equation I'm going to use. Now, uh, since we will be discussing on the concept of energy, so look at the system and you will find out that how the system stores energy at in which forms. First of all, you can see that there is a spring and there is a mass. The mass can store kinetic energy and the spring can store potential energy. So the total energy of the system, okay, is a collection of the energy of the spring and the summation of the energy due to the spring and the energy due to the mass. So the total energy of the system is the summation of kinetic energy plus potential energy. So let's write the expression for energy for that example. And actually, we are going to analyze the condition of stored energy for this mass spring system, and uh, we want to evaluate that how this energy behaves with time. Okay, that what will happen to the energy with respect to time when the time is going towards infinity. So the kinetic energy stored in the system is half, kinetic energy is stored in the mass, so half m is the mass, half m, and it's into acceleration, so x dot square, actually half mv square, and x dot is the linear velocity. If x is the displacement, then x dot is the velocity. So half mv square, so that's why x dot is the velocity, that's why x dot squares whole square. And you know that we have already assumed the state variable x1 is x, which is the displacement, and x2 is the velocity, which is x dot. So thus the kinetic energy equals to half, in terms of state variable, half m, x dot means x2, so half m x2 square. What about the potential energy? The potential energy is stored in the spring. So spring can store the potential energy. So the expression for potential energy is what I'm going to write. The potential energy stored in the spring half spring constant in OK, and spring can store the energy in terms of displacement, so half displacement is x, so x square, and x we assume as x1 as state variable, so uh, thus the potential energy half k x1 square. So the total energy of the system is thus addition of potential energy plus kinetic energy. I'm talking about the mass spring system, what I had drawn already. you had seen in video 1 for the first part of the Lyapunov stability theory. So the total energy say it is W. So W equals to half kx1 square plus half m x2 square. So potential energy plus kinetic energy. So W equals to, if you take half and half, if you take half as common, then it will be k x1 square plus m x2 square. So this is the energy, this is the expression of energy for this given system. This is the expression for the energy, right? And you can see that the energy expression depends on the state variable x1 and x2. In this case also, you can, this, for this mass spring system there are two state variables, and the energy is also depending on these two state variables. Okay, so what about the rate of change of energy? If I want to find out, say ultimately you are going to find out that what happened to energy when time tends to infinity. So in this regard, uh, we may bring the concept of rate of change of energy. What will happen to rate of change of energy? I mean, what happens to, if I want to say about what happens to energy when time tends to infinity, then what about to the rate of change of energy? So rate of change of energy is nothing but the derivative of the energy for energy W. So the rate of change of stored energy is dw, derivative of this with respect to time. So it will be, so partial derivative, so k into 2x1 into x1 dot, sorry, let me write it once again. So dw by dt equals to half k into 2x1 into x1 dot plus half m to 2 x2 into x2 dot, so half, so 2 will be cancelled, so ultimately the rate of change of energy will be dw by dt equals to k x1 dot plus m x2 dot. Now you can remember that we already know the equation of x1 dot and x2 dot. X1 dot is the first state equation and x2 dot is the second state equation, and it can be found from this, x1 dot we have x2 and x2 dot equals to minus k by m x1 minus f by m x2, because I am considering the same example. So I am going to put this x1 dot and x2 dot from the state equation, and let me write the state equation once again. So I'm going to put this expression of x1 dot and x2 dot in this rate of change of energy expression. Let me go to the second. Let me rewrite the expression for rate of change of energy once again. I'm going to put the values of x1 dot and x2 dot in this expression. x1 dot is equals to x2. What about x2 dot? Equals to minus k by m x1 minus f by m x2. So m will be cancelled. It will be minus k x1 x2 minus mm will be cancelled, so it will be f x2 square. Again you can see that kx1 x2 and minus kx1 x2 will be cancelled, so the rate of change of energy will be minus f x2 square. Is it alright? Now we know the values we have assumed already. You can see in the lecture, like video 1, we have already taken the values of the constants. M equals to 1, f equals to 2, and k equals to 2. So let me write the expression of energy once again by putting these values. So it will be W 2x1 square plus x2 square. So it will be W equals to x1 square plus half x2 square. Now we already know that the initial condition already we assume. Not assumed, actually it's given. The initial condition we know for this example is x1 0, x2 0, which is given as 1 1. So what happened when the state variables are at the initial conditions? What happens to energy when at the initial condition? So I can find out by writing W0, because W is a function of x1 and x2, of course. So when time equals to 0, then what will happen to the energy when at the initial condition? So at initial condition x1 0 is equals to 1 and x2 0 is equals to 1. So you can put x1 in this case. I can write down as x1 0 whole square plus half x2 0 whole square. Now what happened to energy at initial condition? x1 0 is given as 1, so 1 square plus half 1 square, so it will be 3 by 2. So initially the energy was 3 by 2. Initially when time equals to 0, the energy is 3 by 2. due to the initial condition, due to the initial values of the state variables. Now we are interested to find out that what will happen to this energy when time is going towards infinity. This is the initial time, initial energy means initial at initial time. What will happen to the energy when time tends to infinity? Initially you are finding out that at initial point, at initial time, the energy is found to be 3 by 2. Now it will be increased or decreased, and you can see that from the practical perspectives that when there is no external input, uh, if I okay, if I say this, if there is no external force, so ultimately the spring energy, that I mean potential energy and kinetic energy will be dissipated along this surface as a heat, because friction is there. So if it is not dissipated, that means that the energy is not decreased. If there is a dissipation of energy, I mean it will happen because there is no external force, and since it is moving up just left and right, so ultimately due to the friction, the potential energy and kinetic energy will be dissipated as a heat due to the friction. So now my point is that initial, however, at the initial, due to the initial points is the cart is moving left and right. So initially there may be energy, but the energy is going to dissipate. That means the energy is going to decrease. If it is so, then it is stable. Otherwise, not. If it is so, then I can say that this system is asymptotically stable. Asymptotically stable means that the energy approaches zero. I mean, there is no stored energy when time tends to infinity. This is actually the concept of asymptotic stability in the sense of energy. So this is the energy expression at the initial point, with the initial time. Now what will happen? See, actually, if you can see, if I draw this energy function on the phase plane. Now energy is a function. Of course, energy is a function, because this W. Let me write this energy function once again in using blue sketch pen. This W, I have written here already above that W is equals to x1 square plus half x2 square. Now see, W, x1 is a state variable and x2 is a state variable. So W depends on the variable x1 and the variable x2. So I can say that W is a function. So this function depends on the value of x1 and x2. So on the other hand, I can write down W x1 x2 as a function, which is equals to x1 square plus half x2 square. So W is a function, right? And this can be, if it is a function, then it on the x is a function. Since the function is depending on x1 and x2, then we also know that the phase plane is constructed on using x1 as x-axis and x2 as y-axis. So this function can be plotted. This function can be plotted. You can see. Okay, let me draw the phase plane. Now W is a function which is depending on x1 and x2, and I have drawn the phase plane considering x1 and axis and x2 axis. So so that function can be drawn. This the W, which is energy function in this case, this can be drawn on the phase plane. Now can you recall this type of the function? Is it a circle or ellipse? It's x1 square plus half x2 square. Is it circle or ellipse? It must be ellipse. And you can see x1 square plus half x2 square. So you can from HS mathematics you can say that which one is I mean the ellipses look like this or this. See, since this is half x2 square, so ellipse must be like So this is the ellipse function, which is energy function. This is the energy function. It's a two-dimensional plane, right? Phase plane is a two-dimensional plane. Now this is x1 and this is x2. Remember, this is x1 and this is x2, and the initial point is given as when time initial point means initial condition mean when time equals to 0. That's why x1 0 means actually we write that state variable as x1 t and x2 t, because state variable is always a function of time. But when x1 0 means that when time equals to 0. So when time equals to 0, the x1 value is 1. When time equals to 0, the x2 value is 1. So do not be confused that x1 0 means that x1 when time equals to 0 and x2 when time equals to 0. So when initial time t0, when time t equals to 0 means initial time. So initial time the x1 value is 1, and at initial time the value of x2 is equals to 1 on the phase plane. So and x1 x2 1 1 means it has some it has a coordinate 1 1 on the phase plane. Where is 1 1? Where may be 1 1 point? Is it here or here? It must be around this point. It is say 1 1 initial point. It's 1 1 initial point. One thing, you do not be confused. This is not phase plane trajectory. This is the function of energy, because the function we are finding out that the function is ellipse. So ellipse can be drawn on the phase plane, but this is not the phase plane trajectory. This is a energy function. This is the plot of the energy function, which is found to be ellipse on the phase plane. Now initial point is there 1 1 given to you already. Now you know that your phase plane trajectory will start from initial point, and it may go to or may not go to equilibrium point, but it will start from the initial point. Alright. Now can you remember that when I discussed about the various types of singularity? There are various types of singularity. When the eigenvalues are in the left hand side, when the eigenvalues are on the right hand side, when the eigenvalues are lying on the imaginary axis, when the eigenvalues are one eigenvalue is lying in the negative real axis, and another eigenvalue is lying on the positive real axis. So for various cases of locations of eigenvalues, the phase plane trajectory may converge or diverge towards the equilibrium point. Now for this example, you can check it out, because m equals to 1, f equals to 2, and k equals to 2 is given. You can check it out. Your equations is also given, your characteristic equation is also given. If you put the value of m, f and k, you have characteristic equation. You can take Laplace transform on both sides, and you can have the characteristic equation in S domain. You can find out using Sridhar Acharya, you can find out the roots, or else you also have a matrix already. This is the a matrix, and you know the eigenvalue for so to find out the eigenvalue you have to solve the characteristic equation, which is si minus a equals to 0. Determinant of si minus a equals to 0, a is given, so you can find out the eigenvalue. And let me tell you that this is a stable system, and from my experience I can see, but you can check, you can find out the eigenvalues. The eigenvalues are found to be in the left hand side as a complex conjugate, but you can check it out by yourself. Your A matrix is given, so you can find out determinant of Si minus A, can solve it and find out the values of S. There must be two eigenvalues, and you can find out that the two eigenvalues will be located in the left hand, somewhere in the left hand side of the S plane, as a complex conjugate. So you know the poles are lying, or eigenvalues are lying in the left hand side, the system is stable. And for this case, I had explained that how to draw the phase, what is the phase type of phase trajectory for the eigenvalues when they are located in the left hand side of the S plane. You can check it out my earlier videos for phase plane trajectory, right? So let me draw the phase plane trajectory for just for this case, because this is also a stable system. The eigenvalues will be found to be at the left hand side of the S plane as a complex conjugate. So if the trajectory starts from that initial point, and it will try to go try to converge towards the equilibrium point, and equilibrium point in this case is found to be, you can also check it out by find you know how to find out the equilibrium point using the slope of the trajectory by checking that dx2 by dx1 is for which values of x1 and x2 dx2 by dx1 is found indeterminate. That's how we can find out the equilibrium point location. And in this case, from my experience, I can say that this is the origin is the equilibrium point. So the trajectory, let me draw the trajectory. Let me will try to move around, and since there is an initial oscillation, because from practical perspective the system will oscillate to left hand side or right hand side, so their trajectory will also oscillate around the equilibrium point. After some oscillation, because energy will be decreased when due to the friction, then also the trajectory will also try to come back to origin towards the equilibrium point. Now you check, this is the orange color is the phase plane trajectory, and the blue color is the energy function what I have drawn. So at initial point the trajectory is here. Okay, now when the trajectory is moving and following this direction, when trajectory is that point, there should be a x1 x2 value. When the trajectory is at that point, there should be a x1 x2 value. When the time is running, trajectory is also moving. When the time is running, let me repeat once again, when the time is running, the trajectory is also moving. And when the trajectory is at that point, there should be another value of x1 x2. When the trajectory is here, the values of x1 x2 will change. So ultimately the trajectory is meeting at the origin to converge, and ultimately the value of final value of trajectory is 0 0 at the origin. So at this is the ellipse when the value of x1 and x2 is 1 1. So that's the initial point. Now when the trajectory, see the direction and the tendency of the trajectory trying to decrease, right? It's a two-dimensional figure, right? And you see, suppose if I take any point, let me take this point using a green color. Say if I am taking that point, this for that point also there should be a proper a specific value of x1 and x2, because this is also a point where you know the values of x1 x2 will there should be a specific value of x1 x2. And say this is value of, obviously it is decreased, so say if it is 0.75 x1 is also 0.75, x2 is also 0.75. so if I have the values of x1 x2 0.75 I can also find out the energy if I put a 0.75 into and 0.75 here. And obviously if it's for 1 if it is t by 2, then 0.75 it will be decreased. Obviously that in that case that will be not w0, because the time is running. There should be a time here also, because you know let me take another sketch pen of different color. This initial point is starting point of the trajectory. At that time there is a time, you know, at this is the initial time t0. Okay, t0 is the initial time, t0 is the initial time. But when the trajectory is now at that point, there may say the values of x1 and x2 is 0.75. Now the time has run already now. So at that point also some values of time should be there, but that value of time is not t0, it's not the initial time, but some specific values of time, right? So let me consider this as t1 time. So what will happen to at t1, what is happened to energy at t1? So how do I write this? So I can write down now in bracket is not the initial time, it's not, now time is t1. So at t1 equals to, and t0 is the initial time, you know, t0 is the initial time which is assumed to be 0. Yeah. That's why it's I've written w0. But wt1 is, again the function is same. This is a function which is coming from the energy concept, potential energy plus kinetic energy, and I can write it down as x1 at time t1 whole square plus half x2 at time t1 square. So now at time t1, I assume that at time t1 the value of say value of time t1 say time t1 say is not time t1 is not 0. So time t1 has some specific value. Say it's a 3 second. So at that in such case I can write down the energy function at w 3. 3 means 3 second. So x1 at 3 second plus half x2 at 3 second. Now at 3 seconds say the values of x1 and x2 say however it is found from a specific graph paper, but I am just assuming that at values of t1 at t1 x1 is 0.75 and x2 is also 0.75. However, these values of x1 and x2 I'm considering arbitrarily, but it is decreased. However, if the starting point is 1 1, it will be decreased. But specific values of t1 at particular time after particular time can be found from the graph paper. So what will happen at time equals to 3 second? So 0.75 x1 3 at 3 second, it is 0.75. So 0.75 whole square plus half 0.75 whole square. What will be that value? 0.75 whole square plus half 0.75 whole square. Let me find out this value. Now you see this is 0.8434 and initially at initial point the energy was 1.5. Now after 3 seconds the energy is now 0.8434. So energy is decreased. If you I am actually, you see I have given I will be given some links of NPTEL video, but in my lectures this is in detail. If you observe and see the video where you listen to this my lecture, then you can easily see that you can easily understand the theory of Lyapunov, because I am discussing these theories in detail. So at initial time, when the time is 0 second, and at the initial time the energy was 1.5, initial time, but after 3 seconds, because the trajectory is moving and taking another point, at that point the energy is now decreased 0.8434. And again, see, this is also a, ellipse. Energy function is a ellipse. So at so energy so ellipse will be also the dimension of the ellipse also will be decreased. So at that point, this is also forming a ellipse, because this is actually the uh, energy is defined by this function, which is a ellipse function of ellipse, right? But the values of the values of energy is decreased when the time is running. Now ultimately the trajectory is going to the origin. So what happened to the energy when at the origin? So at time tends to infinity, so we can write down, so when time is tends to infinity, the final value of x1 and x2 is 0, because ultimately the trajectory is going to the origin at the equilibrium point, final time. So what will happen to the energy at final time? So see, you can again write down the same expression, uh, energy function expression. W, now we can write down t tends to infinity. Okay. Now again, if you write down x1 at infinite time, but at time tends to infinity, the value of x1 0 and x2 0, so it is 0 square and 0 square. So when time tends to infinity, the energy becomes 0. Now you see, so ultimately the dimension of the ellipse is decreasing when the trajectory is also going towards the origin equilibrium point. So ultimately the trajectory ellipse is mixing with the origin. So see, the energy function is energy due to the energy function, it looks like ellipse, but the dimension of the ellipse will be decreasing. Energy is also decreasing when the trajectory is passing, when the time is running. So ultimately you see that ultimately we can say that we can relate the energy with the movement of the trajectory. When the trajectory from the initial point, trajectory is also moving, the energy is also decreasing. So that's why at initial point the trajectory was at highest level 1.5. Then after 3 seconds the energy was 0.8434, which is now less, and ultimately when time tends to infinity, the energy becomes 0. So energy must be 0 when time tends to infinity. That's it. That is the concept of asymptotic stability, and that is how you can determine the stability of the system using concept of energy. Now I can draw another figure for your better understanding. And another point is to be noted is that when the trajectory is moving, is finally at that equilibrium point. At the equilibrium point, x1 is 0 and x2 0. That means there is x1. What is x1? X1 is the linear displacement, which is one of the state variable, and x2 is the linear velocity, which is another state variable. So at the equilibrium point, that there is neither any velocity, neither nor any displacement at the equilibrium point. That's why no velocity and no displacement means though no storing of energy, kinetic energy and potential energy, and that's why total energy is 0. So that is a concept of asymptotic stability with respect to concept of energy. So I hope that you have understood that what is energy function, what is energy, and what is how the energy concept comes from the for a particular system, and what is energy function. And energy function is a function of the two state variable, and energy will be decreased when the time is running. When the time tends to infinity, energy will be 0. uh, Another point is to be noted is that for this example, Let me write down the energy function once again using different sketch pen. Now W, W uh, is the energy function which is function of x1 and x2, and for this example it is x1 square plus half x2 square. Now what is rate of change of energy? dW by dt in this case. I hope this color is not good. Let me pick another sketch pen. X1 dot it is x2 and half 2x2, and x2 dot the x2 dot equation we have already. In this case minus k by m minus f by m x2. Now k is given, f by m is also given, uh, the values of all the values of k and m and 2. What are the given values? So in terms of given values it will be minus 2 x1 minus 2 x2. Now one thing you check, this is my energy function and this is my rate of change of energy. I have explained this example with the concept of energy with a pictorial view, but ultimately we are going to observe some uh, significance of energy function. Initially you see, for this is a function which is always positive for any values of x1 and x2 except the origin. Xy origin means x1 value of 0, x2 0 0, except the origin. For if you take any value x1 minus or plus, or x2 minus or plus, since it is a square, so that's why the energy function is always positive for any value of x1 x2 except the origin, right? This kind of function where it is positive for any values of x1 and x2, it is called positive definite function. However, in my next video, I will explain that definiteness of a function, because it is important. It is required to understand the definiteness of the function for further study on Lyapunov's theory. But for the time being, you just see that what I want to say that is that for any values of x1 and x2, this W energy function is always positive. So it's called positive definite function. This is definitely positive for any values of x1 and x2 except the origin. Now, if I take derivative for this example, for the energy function, and due to the energy state equation, due to the putting the value of energy state equation, the change of rate of change of energy, that is the derivative of the energy function, is found to be negative definite. Actually, it is not negative definite, it is called negative semi-definite. But before I explain in detail about the definiteness of function, that what is positive definite, positive semi-definite, positive negative definite, negative semi-definite, indefinite function, just you, for the time being, I'm just explaining this. Is no doubt, there is no doubt. I hope that you have understand that this is a positive definite function, and why is it called positive definite function. But actually, this is a you can say for the time being it is a negative definite, but actually it is not negative definite, it is a negative semi-definite. In my upcoming videos, I will explain that it is a negative semi-definite. But for the time being, for simple understanding, you just consider this is negative definite. Negative definite means that for any value of x2, it is always negative, because x2, whatever values of x2 minus or plus, it will be square. So before square it is minus, so it is always negative. So derivative of energy function is always negative. However, there is no x1, that's why this the problem is must be there. We will encounter this problem in my upcoming videos. But for the timing, we just watch that for any value of for any value of x2, it is always, the function is always negative. So it is a negative definite function. So from that total understanding, the Lyapunov's theorem 1 comes, or Lyapunov's first theorem comes, that for your if your energy function is positive definite, and if your derivative of the energy function is found to be negative definite, then the system is asymptotically stable. However, stability, what is asymptotic stability, using the concept of energy, I have explained with a pictorial view. But from that observation, the first theorem of Lyapunov's will come. However, I will explain the Lyapunov's theorem 1, 2, and 3 in detail in my upcoming videos. But from that, since we are discussing about this problem-specific mass spring system, so actually the theorem will come from this background. This is actually the I'm discussing about the background of the theorem 1. When I will define when I will discuss about theorem 1, there is a statement of the theorem 1 given by the Lyapunovs. But the statement of theorem 1 is okay, it's a statement, but the concept of the statement of the theorem 1 is coming from this concept of energy. Because if your energy function is positive definite, then if you find out that your derivative of the energy function is negative definite, the system is stable. And obviously the system is stable, you have seen, because energy is decreasing for this example. So we are validating the concept of energy when time is going to 0, when the time is going towards infinity. We are validating with the concept of energy function, which is positive definite, and after derivative is a negative definite. We are validating all these things to establish the Lyapunov's theory. Now at last I am going to draw another figure. This figure is actually a two-dimensional figure, where x1 is a top view. If I consider another figure, it's a three-dimensional figure, where I will consider x1 as one axis, x2 is another axis, and vx or wx as another axis. I mean, I want to consider now. In the next part, I am going to consider a three-dimensional figure where three-dimensional is configured using x, y, z axis. So x axis is x1, y axis is x2, and z is another axis which will denote actually the energy function itself. Let me draw the figure. It will be fruitful if I draw the figure here, because if I go to the next page, then I cannot relate with the new figure with the previous this figure. So I'm trying to accommodate my new figure in this page. So maybe it is a very small, but I hope that you can see the figure. Let me draw the figure here. So this is XYZ, right? Three-dimensional figure. So say, since I have said that x1 is a state variable, one axis, x2 is another state variable, and this is now wx1 x2, which is energy function. Now the same figure, this is a top view on the face plane, right? It's a plane, and if I consider this as a three-dimensional figure, what will happen? Say your point was initial point was 1 1 here, and your trajectory is like moving like this, and at that initial point you have seen it ellipse. So for three-dimensional case, this ellipse will be like this. Now when the trajectory is moving to a new point, then the ellipse will be when the trajectory will be moving to a new point, the ellipse will be solubility is 0. So you can see that you can find more clear figure from your book, that actually this is the shape of the energy function. When the trajectory is passing, the ellipse also decreasing. The ellipse is decreasing means that energy is also decreasing, and this is the figure it takes, and this ellipse at different points of face trajectory, this is values of ellipse, the dimension of the ellipse will be changed due to the change in uh, energy value. 1.5, like at initial second it is 1.5, at 3 second it is 0.8434, at origin it is 0. So that's up to the concept of energy, and I've discussed that how the concept of energy is required to establish the theory of Lyapunov. That is the first theorem. If your energy function is positive definite, your the derivative of the energy function should be negative definite. And when the trajectory is passing the energy function, since this in this case of mass spring system, the energy function is taking as ellipse shape geometrically. So the ellipse is also, the dimension of the ellipse also decreasing, and since the energy is also decreasing due to the various points when the time is running. So in my next video, I will bring some new concepts on Lyapunov stability theory. But before that, I have to discuss about definiteness of function. What is positive definite function? What is positive semi-definite function? Negative definite function? Negative semi-definite function? Then I will discuss about quadratic function, Silver's criteria. Then I will discuss about the Lyapunov second method, or direct method of Lyapunov.